The whole quantum mechanics is applications with details of three sentences, and these three sentences are the following. Sentence number one is that if you have to predict numerical value of any quantity, find its operator. That's sentence number one. Sentence number two is to find the eigenvalue of operator. That's sentence number two. Sentence number three is that eigenvalue is the physical prediction for the numerical value of that quantity. So that's it. You can say whole quantum mechanics. But for that you need to know two things. One is that how to form an operator, and that is I start in this lecture by telling you an operator of momentum, which is actually I have told you already, but in this lecture I tell you how to use that information, momentum operator, for finding its eigenvalue, and that means I introduce the term eigenvalue as well, and then that's it. In this lecture we start with momentum, and then in the next lecture introduce another operator which is parity, and then next I tell you how to form operator for all other physical quantities. So in this way you can see in this scheme cover the whole quantum mechanics. And with that knowledge, the rest of the material in this lecture has certain one definition and three theorems. And the purpose of all this would be to answer this question that if your physical prediction, namely eigenvalues, has to be real, because our prediction should be real, then what kind of operators we should have it. A momentum would be an example of that. Generally what kind of operator we have, and what kind of eigenvector or related eigenfunction. So that's the whole scheme. So now I start detail. And as I said, I start with the momentum operator. And momentum operator, when in position representation, when in position term, when your eigenvector, momentum eigenvector becomes position momentum wave function, namely plane wave, then momentum operator on it, namely derivative on it, gives you, this equation is not new to you, and in calculus that's a very early calculus, exponential remains unchanged, but that's significance of remaining unchanged, that is not, I think, familiar to you, and that is I am telling you now. And that is that if it remains unchanged, that means quantum mechanically this means that measurement does not change the state, function remains function, but multiply with value, and this value is, I give a name of it, which is called eigenvalue. I introduce the name later, but for the moment you just see it. Whatever the value is becomes a coefficient. If it is a constant, it's a value. That is physical prediction. Here we have seen physical prediction for momentum, but the whole quantum mechanics is not limited to momentum. And as I say, I promise the whole quantum mechanics is not momentum. The whole means the operator can be any. It's not necessarily momentum. It can be energy, it can be angular momentum, it can be position, it can be parity, and you name it. So generally you will have, rather than momentum in position terms, we have generally operator. It can be any, and it can be in any representation. That means in terms of any independent quantity. So that's one generalization we have done it. And position wave function of momentum, the limitation, I said wave function, and now generally this is wave vector, and said of momentum, generally of any observable, Observable or physical quantities, measurable quantities are called observable in quantum mechanics. Now, eigenvalue, it's not necessary that you have one eigenvalue. In momentum case, you can say one, but it's actually, even that is not one. If you think of, if you understand that we are doing science, and in science, the results are measured, and the symbol is not measured. The measured are numbers. So you should understand that k is not one, k has large number of values. So in general, values can be many, and here they are distinguished by a discrete letter n. Here it was distinguished by a continuous different values of k. It can be discrete, we can generalize it to continuous as well if needed. But anyway, that's a general equation it becomes. And if I have to teach you the terminology means eigenvalue and so on, I teach through a general equation rather than momentum limited equation. So now we have a general equation. Now we can target learning terminology, and terminology is picked up from matrices. And you can say, what is the relation of matrices to the whole thing? That's the question. And the answer is that this general operator in our basis, this is basis. If we choose a discrete basis, we say psi 1 first. You concentrate on the counting. If we can count first vector, second vector, third vector, your components will also be counted. First component, second component, third component. And the first, second, third component can be rearranged in a column. So you have to memorize that, and sounds make it hopefully job easier. Cat is represented by column. Sound is same, K column. And what is column? What operates on column? The answer is matrix. So A is a matrix. Here is sum. And in matrices, have you seen that? This kind of. Not, then I change terminology, a symbol a bit, and hopefully that will remind you. Rather than psi, call it x, and rather than a, call it lambda. Hopefully you can recall this lambda is eigenvalue, nth eigenvalue, and x, maybe you have been saying it nth eigenvector, but I think I suggest you change your terminology. In this course, you reserve the word vector for eigenvector, namely eigencat vector. And here it was actually, even if you have been calling it vector, but you think of that, it was a column. So I will call it eigencolumn, nth eigencolumn. That's a bit, maybe for some of you it's changing terminology, but that is not changing terminology. You have been calling it eigenvalue, and I still call it eigenvalue. So that's it for terms. If you need a revision, then I write a revision that x is eigencolumn, and generally that's a discrete representation. Generally it's not eigencolumn, it generally is eigenvector. And what multiplies on right hand side is eigenvalue. So that's one terminology conveyed to you. Another terminology is a particular kind of operator, and they are called Hermitian, and that is in the title of today's lecture. So eventually, by the end of this slide, I have to introduce you the word Hermitian, but I start with a condition on values. And the condition is that, remember the three sentences I said, the whole quantum mechanics. The first sentence was that if you have to make physical prediction for any measurable quantity, make its operator That first sentence. Find its eigenvalue, second sentence. And the eigenvalue is physical prediction, that's the third sentence. So what I spoke in English is translated into mathematics. And if you know that we are science, that you should, hopefully you should yourself understand, if not then I tell you, that your physical prediction, which you ask experimentalists to measure, they should not have iota or anything like that. You cannot ask an experimentalist that your energy is 5 plus 3 iota. No meter will measure iota. So if you have to make a science which has to avoid contradiction with the experiment, and simple language, that has to, if that is to be verified by experiment, then experiment will say that values are real. So you write it. Real means its complex conjugate does not change it. If it's iota will be replaced with minus iota, but there should not be any iota. So that complex conjugation replacing iota with minus iota does not change it. Now you better concentrate only on this equation and do not remain limited to the background, is the origin of the equation. Concentrate on equation. This symbol has complex conjugate does not change it. That's eigenvalue. And if the eigenvalue is of a special kind, then operator should also be a special kind. And that means operator should also satisfy something like that. It's not exactly saying something like that. In saying something, here it was real, an operator has to be Hermitian. Don't bother, I have to introduce the word Hermitian. But pay attention to this equation. Here you have a complex conjugate. Hermitian means, and that the word is taken again from matrices, that you take complex conjugate and also use as transpose. And the transpose I write in the next when I show you connection to matrices, and then I write, which hopefully you already know about matrix. But for the moment, pay attention to the situation that so far I have said about operator. Generally, matrices are discrete representation. So first you learn this new thing, operator, and then you come to the familiar, your old familiar thing, which I wanted to show is later. So that first you can concentrate on general thing, but now you go to familiar thing. Familiar thing is dagger. Okay, dagger, the word is Hermitian conjugate, and the symbol, like complex conjugate, is a star. Hermitian conjugate means transpose as well. And when you have represented operator with matrix, then transpose means you change row to column and column to row. And complex conjugate becomes a Hermitian conjugate, and Hermitian conjugate has, at least in matrices, hopefully you know already, that has, in addition to complex conjugation, that has transpose as well. The whole combination is called Hermitian conjugate and is written as dagger. Dagger with, you remember, can you see that it's a dagger? The handle is up and it's pointing to down. So now we make use of connection with matrices to write equations which are satisfied with Hermitian operator, namely the component of representation of Hermitian operator. And if you are a bit confused about what is the word representation, then I show you. Discrete representation is matrix. And if you ask what is the relation of operator with matrix, answer is the following. That matrix has elements. I is row index and J is column index. And this element of a matrix is equal to bracket related to operator, where bra as the same as row index is labeled, and bra cat, and cat is labeled by column index. And again I again see cat to column, that's easy to remember hopefully. Now coming to that's a generally, that's for any kind, this relation is for any kind of operator, maybe Hermitian, may not be Hermitian. But if it is Hermitian, then what? To learn, maybe you start this time by matrix and then generalize it. If you want to start with matrix, then Hermitian matrix definition is that is, if you take Hermitian conjugate, it remains unchanged. So in this slide, I just concentrate on the difficult part of what is said. Now that part is easy. Hermitian conjugate is equal to itself, A dagger is equal to A. Relatively difficult is that what is the definition of dagger, Hermitian conjugate. And that's a difficult thing, and that's all I have space in this slide. This equation I can write in the next as well. That's right in terms of operator as well. Okay, I've already written, sorry. I've already written it. So anyway, concentrate on the relatively difficult part, and that is that what is dagger? What is Hermitian conjugate? Now in matrices this means complex conjugate and transpose. Transpose means row becomes column and column becomes row. Row index becomes column index and column index becomes row index. That's a transpose. Now what you know about matrices? Now you relate to operator, and this becomes you just apply that connection to here. That means row is bra and cat is column, and here row is J, that's bra, and column is I, that's here. Complex conjugate, everything is there, so I don't think that there's anything new. So I think you have no problem if I just write now formal definitions of Hermitian operator. No, you may think this Hermitian operator definition is written here and it is formal. The reason it's not formal is that so far we have a special kind of cat and bra. In the formal general definition, that limitation is removed. You can have any cat, any bra, and the definition is valid for any cat bra. And if you make that generalization, then you have that. Namely, what is dagger? Hermitian conjugate? Is that's a question. Answer is that you make a column. First we transpose column as row and a row as column. That's a difficult part, transpose. The next is simple. Whatever the result, you take complex conjugate, and that's a difficult definition of dagger, Hermitian conjugate. Once you have learned it, the rest is simple. If you know a dagger, what is Hermitian conjugate, then the definition of Hermitian operator. Be careful. First definition was of Hermitian conjugate, and now the second is Hermitian operator. And the whole difficulty is in the first. If you have learned the first, then the second becomes very simple. Then A dagger is equal to A. In word, you take a Hermitian conjugate and it does not change. That's it. So I have split the definition which I promised into two definitions, and the main difficulty is put in the first definition of Hermitian conjugate. So you have to be careful about making sure that if you are defining Hermitian conjugate, you are defining Hermitian conjugate, not Hermitian operator. And you are defining Hermitian operator, you are defining Hermitian operator, not conjugate. So that you have to memorize this definition. So once I summarize whatever learned. We have summarized definition of eigenvalue, eigenvector, Hermitian conjugate, and Hermitian operator. With 4 definitions, we are ready to give you some information. Definition are just cultural, scientific cultural decisions. They are not information. Now, informations can be scientific laws, or if they are proved, they are theorem. And what I have to tell you in this lecture are theorem which are proved. And theorem are 3. The first of the 3 theorem is that Hermitian operator, which I have introduced through a demand, and the demand was that the eigenvalue should be real. But demand was just actually, if you pay attention to it, demand was just spoken to introduce. That was not proved. So when I prove it, that's the first of the 3 theorems in this lecture. So, you understand? The first theorem is that if operator is Hermitian, that eigenvalue are real. And real means they are measurable. So that's a claim, that's a theorem. Proof starts with here. Since the theorem is for Hermitian operator, first you write the definition of Hermitian operator. A dagger is equal to A. Remember, it's not Hermitian matrix. It's Hermitian operator. Is a hat tells you. The next step, what you do is you take the equation and you multiply a cat in the sense of cat bra. You multiply both sides with cat. Psi n here, psi n here, psi n here, psi n here. Hopefully you can see that. And the left hand side, namely bra, you multiply both sides with psi m bra. Psi m bra here, psi m bra here. That's how written. So, simple. So next what I do is, right hand side is unchanged, and in the left hand side I have introduced definition of Hermitian conjugate dagger. Can you recall what is the definition? Definition has 2 things. First is transpose, column becomes row and row becomes column. It's a difficult part. Easier is that you take complex conjugate. So that's it. Now, you remember, so far we have not said that these are eigencat. So far I have used only definition of Hermitian operator. And now eigenvalue I introduce. And that is, if I say that psi n is an eigenvector of, right hand side is easier. So better start with right hand side. If I say that psi cat is eigencat of operator, then you recall what is the definition of this time, definition of eigencat or eigenvalue. And the definition is that operator is replaced with eigenvalue. Eigenact remains unchanged. So dot product and eigenvalue is a value, I can take it outside bracket. The right hand side was easier. Left hand side is more difficult, but I hope only slightly more difficult. There are 2 difficulties. One is maybe only psychological, nothing logical, and that is that rather than letter N, you have letter M. That hopefully is nothing new, nothing. Something new is that you have a complex conjugate. So whatever you get, you take complex conjugate throughout. So that's it. I go next step. And that is that, here cat and bra are interchange. Psi n is cat, here psi n is bra. That interchange I can compensate by interchanging cat and bra, and for interchanging cat and bra you need dagger Hermitian conjugate. And I can introduce it. I can replace complex conjugate by Hermitian conjugate. Justification is the following, that in Hermitian conjugate, dagger, you have transpose as well. But if it's a number, you take transpose or you don't take transpose, it's the same thing. If it's the same thing, you must be wondering why I have introduced a you may say, more complicated things in Hermitian conjugate rather than simple complex conjugate. That's the question. Answer is that only for Hermitian conjugate we can interchange cat and bra. We can make cat as bra and bra is cat. And remember why I have done it? So that I get the same thing on left hand side and right hand side. First I write it and then I tell you what's the advantage we get out of that. First I just write what I've spoken. I've just, nothing else I've changed except that I've introduced dagger, and here means cat has become bra and bra has become cam. Why I've done it? What was the aim? What is the plan? And the plan is simple. Now these things have become same. The difficult things have become same. Now that's one equation, and I said in this lecture I'm introducing 3 theorems. 2 of them are actually implications of this just one equation. So don't say it's for one theorem. This one equation is for 2 theorems. And 2 actually are logically 2 cases as well. And the first case is that n or m are same. If n or m are same, first you replace everywhere m, n, m, n, here m, n. Done it? If you have done it, just think of that. What do you recognize what is that? That's a dot product of a state vector with itself. Normalization says that's 1. If it is 1, whatever is the lengthy, you may say complicated mathematics, that becomes very simple. This is 1, this is 1, this means just you have numerical value. An star is equal to an, because that is 1. So, in words, what we have proved it, that these an are eigenvalues, and these conditions they are eigenvalues are real if operator is Hermitian. That's the theorem number 1. And now is the time for theorem number 2. And as I said, the theorem number 2 is also follows from this one equation. So for comparison, for ease in convenience in seeing it, I have rewritten this equation again in the next slide. And I have also rewritten that in the next slide. So, you see, just I have written it. Now, why I have rewritten? This is a question, and the answer is that this time I want to prove a related theorem. And that's the theorem number 2. You know, I said 3 theorem, I have to say. So, theorem number 2 is, a statement of the theorem is the following. The statement is that eigenvectors of a Hermitian operator belonging to different eigenvalues are orthogonal. So now start proving it. In proof you write 2 equations which are already in the previous theorem as well. Just rewrite it, and then you start journey toward this new theorem. The first step is that is only psychological. Logically nothing new, that you replace letter n with the letter m, and psychologically you may feel it's a new information, but actually logically it's not, because if you understand that we are doing science, then you must also realize that in science eventual results are predictions, and prediction has to be of numbers. So that symbols are actually our tools. Symbols summarize numbers. N summarizes 1, 2, 3, 4, 5, 6, 7. M also summarizes the same. So as a science, 2 equations mean the same thing. So that's the justification. The next question is why I am doing it, and to get that you just see equation 1, and if am star is am, I just replace am star with am. I have spoken and now I show you in writing, with writing I do two things more. The first is I take a case when m is not equal to n. You know, in the previous slide I took the case when m was equal to n. So pure logic will say that the remaining is that if m is not equal to n, and then what happens to equation 1? I have just spoken. You just replace am with am star with am, and you collect all on left hand side. So am, not star, remember, because of here. Am minus an, this is same. So I have collected here everything on left hand side. So the purpose of doing this left hand side right hand side interchange is that now we have two factors, and now pay attention to the statement of, namely the condition of the theorem. Eigenvalues are different, and can you recognize there are eigenvalues? Eigenvalues are an or am. If they are different means they are while I speak I think I better write as well, you can see that. If they are different, different eigenvalues, different a and m, the difference is non-zero. If this is non-zero, the first factor is non-zero. If the first factor is non-zero, the second factor is zero. So, can you see what we have achieved? The second factor is dot product. If dot product is zero, that means they are orthogonal. So that's it. That's what we have to prove. That was our target, and we have achieved it. Let me see if I have written something else as well in this slide. Okay, I have written the statement of the theorem in symbols, nothing else. And that means that, what it said, different eigenvalues, if an or am are different, eigenvectors in this, during the proof I have given the name of two eigenvectors, namely psi n and psi m. Eigenvectors are orthogonal, that means the dot product is zero. And if all this is true, if operator is Hermitian. So that's it. What I've spoken in English, I have written in symbols as well. Nothing else. I was looking for the last sentence is nothing new. It's just a summary, but already spoken. The conclusion was already reached here. If you understood symbols. If you not understood symbol, I've revised for you. So remember how many theorems we have covered? 2, and I promised 3. Where is the third? Third is here. To introduce a third, what I do is that I take you to ordinary vectors. You remember, you have been thinking that you are, I don't know, if you are amongst the person who are still confused about cat and bra, then I give you a shorty and try to use it. And the shorty is that cat and bra are also vectors. So if you are comfortable with ordinary vectors, but if you are not comfortable with cat and bra, then try to understand. And I give you example and maybe more example in the lectures to come. That what if you have any difficulty in any new result for cat and bra, I can assure you, I think I can guarantee you maybe that result will be available in ordinary vectors as well, where you are comfortable. For example, for a ordinary I unit vector and j unit vector, I think more simple vectors are not perhaps possible. Here you know two things. One, that they are orthogonal to each other. In that case you have been calling it perpendicular, but now do not use the terminology of perpendicular, because in this next application we have to replace it with cat and bra, and cat and bra cannot be perpendicular, but they can be orthogonal. So better use the equivalent available terminology of orthogonal, so that you can have a transition to cat and bra. So when you have learned that, replaced the terminology, Then you recall I dot j is equal to 0. That means I and j are orthogonal to each other. That's one information you have. Another information is that I and j form a basis. Basis means any vector can be written as their linear combinations. So that is for ordinate vector, and I would say same. If you are not comfortable, you can say similar. Result is valid for cat and bride as well. You know, when I say same, what is that? If they are orthogonal, and we have proved in the last previous slide that they means Hermitian eigenvectors of Hermitian operator. They are orthogonal, although there is a condition as well for different eigenvalues. But if you want to learn from here, then for the moment do not be distracted by condition, and better concentrate on the result that eigenvectors are orthogonal. So the condition 1 is also for eigenvectors. Now, if information 1 is also valid for eigenvectors, is information 2 also valid for eigenvectors? Answer is yes. And here I don't have time to prove it. I give you only a reference, and I think the reference also doesn't prove it, but at least you can see that it's published. And in the published, if you ask me where it is published, the answer is that's a book which quantum mechanics, concepts and applications. That's the title of the book. Is written by Nuruddin Zetli, and that's a book I have been following in this actual teaching, which formed this lecture series. In actual teaching, for application, for problem solving and exercises and examples, I use this book. And this book has theorem 2.2, and the statement in this book is equivalent to that statement that eigenvectors of a Hermitian operator form an orthonormal basis. And you see, that's all I have said here. Eigenvectors of a Hermitian operator they form a basis? Yes, they form basis. That the word is there, orthonormal basis. That should not be new to you. Orthonormal means orthogonal, and orthogonal I have shown it here. And normal means the dot product with itself is equal to 0, and that is nothing new. I have used it in 2 slides ago as well. That psi n dot product with psi n is 1. So the theorem should be familiar to you. Now I have only one piece of one slide remaining before conclusion, and in that slide what I do is that I apply the 3 theorems taught in this lecture to momentum, so that I make this theorem somewhat familiar to you. Somewhat you can see their application as well. Application to momentum. So can you recall what the 3 theorem we learned? The first theorem has been that eigenvalues of a Hermitian operator, and I can tell you only state, I don't have time to give you proof. That the proof is in the same book which I said, Zetli, or in any other standard quantum mechanics book, that this momentum operator is Hermitian. That I only state as a new information now. But which is not new is that I've told you that eigenvalues are real. And in case of momentum, you can verify. Eigenvalues are h bar k, and they are real. That's theorem 1. Theorem 2 has been that eigenvector in momentum case by eigenfunction for different eigenvalues are orthogonal. That's the theorem 2. And if you apply that to momentum, then the proof you start from here, A dot B. B should also be italic. Sorry, it's a bit of typing lapse. So A dot B is equal to AX BX. This in direct notation becomes dot product is written as cat, and the summation is that, and rather than 1, 2, I said any sum. That's nothing new. I've shown it before in previous lectures as well. If you have not gone to previous lecture, you should see it's nothing new. This is ordinary lesson of vector which I have written it in cat-Brown notation. Nothing should be. It's only symbols are new. Now next what I do is rather than summation over discrete I replace I with continuous x. That means the summation will become integration, and rather than discrete components, I write continuous functions. And what I do is that cat is k and bi means kx should be, and kx is a kii replaces x, and b replaces k. Kx means a function of x. Here you can see it's a function of x which is labeled by k, which has one wave length. Remember what kind of wave function is that which has one wave length, and that is plane wave. So bi is a plane wave, that ai is on the left hand side. What you have is, I have to take complex conjugate, so iota becomes minus iota. So that's the dot product. And theorem number 2 says that if eigenvalues are different, means k and k prime are different, then dot product is 0. And the justification is through calculus, and I don't have time to teach you calculus here. I can tell you the result, and you can memorize that result as an additional integration formula. Like previously, by that time most of you would have only memorized it. Maybe you have forgotten proof of integration formula. What you memorize? Power rule, or trigonometric, or exponential, or trigonometric, or whatever. So add to that a result that if your integrand has e power iota, and the limit of integration are actually, when you sum over x, then all possible values of x are minus infinity to plus infinity. So this integration, now if it is not iota, then you can take anti-derivative ordinary way. But if you take anti-derivative ordinary way, you put upper value and you put lower value. If it is real, you do it and you will get a usable result. But if it's iota, think of that. When you put upper value, it will be e power iota infinity, minus iota infinity. So that means that is not useful. So the calculus teacher can tell you, or maybe now calculus book can tell you, or maybe some website can tell you, or say, I try to just tell you the result. That if you are integrating e power iota, then integration result is proportional to direct delta. Now that's a calculus. Now our immediate problem is that if eigenvalues, you remember eigenvalues are different, that means k and k prime are different, then it's a simple property of direct delta that if input is non-zero, like direct delta, if you have I minus j is non-zero, if you canonical delta as well, if k and k prime is non-zero, the answer is 0. And answer means here is dot product. You know, dot product is this is a dot product. Hopefully you can see that. The whole thing I've repeated in 3 different ways. The dot product is 0, and if this dot product is 0, that means their eigenfunctions are orthogonal. That was the theorem 2 verified for momentum. And remember what was the theorem 3? Theorem 3 means that eigenvectors form a basis. Because for momentum we don't know eigenvector, we know eigenfunction. So the eigenfunction form a basis as well. So you know what basis means? Basis means sorry, a bit of a mix of animation. The result which I have been speaking has appeared now. I should there's no typing error but animation error. So I give you time. I repeat it with that with this summation. I repeat with this appearance of that. Nothing new. The summation b I replace with k and a will be k prime. The summation becomes integration, and this kx means a function which is labeled by k, means plane wave, and here it is replaced with k prime, also plane wave, and the calculus says it's a direct delta, and that's 0. So that's just only animation appearing now, nothing new. Sorry for that animation interchange. And now I go back to what I was saying again, and that is that the third theorem. The third theorem says that if eigenvalues are different, the third theorem is that whatever, different or same, the third theorem says the eigenfunctions, namely these, form a basis. Now basis means what? I show you. Hopefully animation works now. Yes, it has worked. And that is the basis that I showed you in previous slide as well. Make it for ease in convenience, I've shown it again. That's the definition of basis, the first. But only new thing I've done is I've introduced different colors. I and J are basis, and now in quantum mechanics the basis is, the theorem says that basis can be eigenfunction of any Hermitian operator. If Hermitian operator is momentum, then basis is not Ij but plane wave. That's the blue. And the vector generally is any wave function. Any vector can be written as a linear combination of bases. In case of momentum, that means any wave function can be written as a linear combination of momentum basis, momentum eigenfunction, or plane wave. 3 words for the same thing. Now the rest of colors are telling you what? Plus is sum, and sum becomes, we don't have 1, 2. I've said it, all continuous value of k. So that means continuous means the sum is integration. And the coefficients, they depend upon which basis you have, basis vector you have. If it is the first, you have a first. I could have written it v1 I, v2 j. 1, 2 are discrete index, and I replace with continuous k. That depends upon 1, 2, and 1, 2 is replaced with k, so that means a function of k. And you recognize what is that? That's a wave packet. So the result is already, you know it. So wave packet means what? Wave packet means any wave, any wave function can be written as a linear combination. Means add, you do a plus, and plus is integration. So result is nothing new. If you have studied quantum mechanics, and if you have studied mainly only mathematics, then for those of you who are more in mathematics and studied less quantum mechanics, for then I tell you that if you take t is equal to 0, this becomes what mathematicians know as Fourier transform. So result is nothing new. Only nothing new is that I've indicated that result is wave packet or Fourier transform is verification of our third theorem of this lecture for the case when Hermitian operator is momentum. And I can only tell you the momentum is Hermitian operator. And that's it. And I conclude, and then I finish. The conclusion of the following. First we learned it, what I started the lecture with saying that quantum mechanics is 3 sentences. The first sentence, and that I've written it here. So maybe I not be spending time on it. The same sentence I've written. That measurement gives you eigenvalue, and it was understood that eigenvalues are real, and what we learned in this is that if eigenvalues are real, then operator must be Hermitian. And I've introduced definition of Hermitian, and introduced definition of eigenvalue and eigenvector and all that. That's the first part of this lecture. And the second part we proved theorems, and first theorem was this is written here, that if it is operator is Hermitian, then eigenvalues are real. That's the theorem number 1. Theorem number 2 was that if it is operators are Hermitian and eigenvalues are different, then eigenvectors are orthogonal. The dot product, the bracket is 0. And the third is that if they are orthogonal, that like an ordinary, then like ordinary I and j, these orthogonal things, this means eigenvectors form a basis. You can write any wave function in terms of their linear combination. So that's all in this lecture, and thank you for watching it, and I say goodbye here.